Okay, welcome everybody. Today's webinar is about erosion and deposition in rivers, which is a very important topic for a lot of river restoration studies and engineering design of riverine structures. Um, Before getting started with the topic itself, I want to share with you a few news we have. Um, as I said, this is our last webinar in the year. We are very happy about the outcome of these webinars this year. We have had 10 open free events in 2015 in a wide variety of topics in our area of expertise, including two-dimensional riverine hydraulics, hydrologic modeling, pollutant dispersion, oil spills, two-dimensional modeling, sediment transport, and also we had a webinar about the integration we are doing with Autodesk InfraWorks 360. We have had more than 2,000 attendees, including those who have registered for the webinar, but also those who have watched the videos afterwards. This is a record in our attendance this year, and we hope that you have found our events interesting and productive for your work. Also, we are very excited to share with you the news about last week, Autodesk University. Autodesk University is a huge event that occurs every year in different countries. In this case, we attended the event in the United States, and I had the privilege to give a class on the integration of RiverFlow2D with InfraWorks 360, which is codenaming Project Boulder, with Matthew Anderson, that is a product manager at Autodesk. It was a very, very interesting experience. And we had the class on Project Boulder, very good attendance and a lot of interest on what we're doing. And I want to also share with you a video of what you can do with InfraWorks 360. And let me show you, it's a short video, less than a minute or so. And this is a city of Portland. And this was done by Jason Thomas, who is a consultant, and he shared it with us. And as you can see here, with InfraWorks, you have full three-dimensional work environment. And it's very unique because you don't work in 2D. You work everything in 3D, and you can directly run the model from there and show the results in a very impressive way, which is of use for very important for presentations and showing the model results for different audiences. So all this you can do with the InfraWorks 360, and it is a tool that is now available for free, and it will be available until June next year. In using the Autodesk Lab site, you can access the Project Boulder, and you can download the InfraWorks 360 and all the software necessary to do the testing you may want to do. You have also more information at the Hydronia website on how to use it, and you can email me if you are interested in this. Okay, now about the topic of today's webinar, which is erosion and deposition, sediment transport. Again, sediment transport, as many other processes that occur in rivers, is a challenging phenomenon that you need to model, and to model in 2D has several hurdles that you need to overcome. First, as in many riverine situations, you have high velocities and regime changes, supercritical, subcritical flows. So you need to handle that things with together with the complex terrain that may have very uh, um, gradients of the topography and so forth. Also, the boundaries can be irregular, and you have a wide range of sediment sizes. So you may have gravel, fine sand, and so forth, and that should be accounted for in the model you wanted to use to um, simulate erosion or deposition. Also, the changes in the riverbed can occur slowly or they can occur rapidly. It depends on which river you're handling. If it's, you know, it's a plain river or it's a mountain river, they behave very differently. Now, today's webinar, I will start with a Sediment Transport 101, or I should call it 001, because it's a very, very, very short and basic introduction to sediment transport, or what you should know or need to know to be able to apply a model, sediment transport model. I will then talk about how we implement erosion deposition modeling using RiverFlow2D. And I will show you how to set up a complete two-dimensional sediment transport model using RiverFlow2D. This will end in a visualization. I will show you how to visualize erosion deposition patterns in the example we are going to run. Very brief introduction to sediment transport hydraulics. As I said before, we in nature we have a wide range of sediment sizes that are characterized by size classes that can go from very fine sediment, clay type sediment, really fine, up to the boulder size, which is a huge meter size particles. Now, in general, in riverine environments, we are dealing with a range of sediment usually that go from the very fine sand range to the gravel size. Although, of course, if we have the need to model very fine sediments, we can do that too. But there are some situations where this very fine sediment require cohesive treatment. So they behave as cohesive sediment and they need special treatment. So this is the range we are usually covering in sediment transport in riverine environments. Now, this is a picture I took several years ago, but it shows the wide range of sediment size that you can find in the same, even in the same river in different events. So you see here, it's the marginal side of the river, and you see different strata showing different compositions of the sediment. Some of them look to be very fine. Some of them have coarse gravel-sized sediment embedded in the bed. So it depends on what's the source of the sediment that's being transported by the river. And when the river floods the floodplain, the overbanks, that sediment is usually deposited there, and it creates these features when it's eroded back into the main channel. So you need to have a model that is capable of handling different size fractions to accommodate this erosion and deposition patterns. Now, of course, depending on the size, you may have size of the sediment, of the particles, you may have movement or you may not have movement, depending on the flow velocity, the shear stress, etc. And there is a diagram, it's called the Shields diagram, that can be used to determine if a sediment particle can be incorporated or moved by the flow or not. And this is called the Shield diagram, and this is the Shields curve. This is the Reynolds number. There is a function of the sediment particle, the viscosity, and And also this is the critical shear stress that is a function mainly of the shear stress that the fluid exerts on the particle density, water density, and also the size of the particle. Now, what is usually done here is that based on the Reynolds number and the critical shear stress, you can determine if you are above the Shields curve or below. And what this means is that if you are above the Shields curve, the sediment is moving. So it's the shear stress that the flow exerts on the particle is able to entrain it into the flow, and it carries it downstream. If the particle, or it's the combination of these two parameters, gives you a point below the curve, then the particle cannot move, either because it's very big or because the shear stress is not enough to entrain it in the flow. Now, there is a common use diagram or example that is called the lane diagram, where you can have all the main parameters or the main factors that affect the erosion and deposition patterns. So this is idealized in this apparatus here, where you have the different factors: sediment load on one side, sediment size, stream slope, and stream discharge. And you see here that you can move these weights based on the different factors. So you can decrease the stream slope, increase the sediment or decrease the sediment size, and so forth. So what this means is that, for example, if you wanted to see what's the effect of decreasing the sediment size, if you move this weight to the left, then this balance will turn to the left and you will go to the aggradation. So that means that the combination of these factors, sediment load, sediment size, stream slope, and discharge, it creates either a propensity for erosion, or that degradation that is also called, or deposition or aggradation. So this is a very simple way to visualize all the factors that are commonly involved in the sediment transport process. A more
Let me show you this video
physical
where
view of it is this
I
video.
think it's illustrative because it shows the movement of particles at different depths on the flow. So the flow is coming from the right to the left, and you can see that there are particles that move much faster on the top and much slower on the bottom, and that gives you an idea of the depth of the bed load transport, and also on the upper part of the particles that move suspended with turbulence that exerts the flow in the particles. So you have different transfer mechanisms that you need to take into account in the model. Now, these transfer mechanisms are typically classified as a wash load, suspended load, and bed load. Now, the wash load is that type of transport of very, very fine particles, and it typically do not interact with the bed, so it does not generate any sedimentation or erosion. The suspended load is that kind of transport that occurs for fine particles, but not so fine, and the particles interact with the bed, so it can generate erosion and deposition, but it does not roll over the bed. It remains suspended for most of the time. The bed load is referred to that mechanism by which the particles move very close to the bed. They roll over the bed. It can jump, but it remains very close to the bed, and it's normally formed by very or the most coarse particles in the size distribution. So a model needs to be able to represent both the suspended load and bed load. The wash load, as I said, is not the kind of transport we are worried about because it does not generate any erosion or deposition except on very flat or very low velocity areas in coastal environments. Now, the suspended load is the kind of, if you could define it, is normally for very fine particles, and it is considered that very fine sand in the range of 0.125 millimeters. So in that range is typically transported in suspended mode, while the bed load is mostly formed by coarser particles larger than 8 millimeters, and coarse sand, gravel. It's all being moved by by bed load process. And clay and silt, very fine particles, they move with wash load. And as I said, it's not of concern to us because it play a very little role in the erosion and deposition processes. So these are the transport mechanisms. How do we determine the transport capacity? Transport capacity is in bed load computations is determined via transport formulas. So there are formulas that tells us what is the amount of sediment that is being moved by the flow. And the imbalance between the transport capacity and the sediment supply determines the deposition or erosion. And this is illustrated in this image here. You see the inflow supply, or the amount of sediment that is coming to a certain control volume, and the transport capacity is what the flow can incorporate from the bed, so that layer on the bottom. So if the supply is greater than the transport capacity, so you have more sediment coming in than out, then you have predominantly depositional processes. And if the supply is less than the capacity, then you have erosion process. So all these play, factors are in the model, and they need to be handled automatically, obviously, because they are very complex and varied in space and time during a specific computation. Now, the transport formulas are based on formulas that provide the amount of sediment as a function of the shear stress on the bed. So the shear stress is something that we cannot measure, but it's normally a function of geometry, roughness, depth, and velocity. And it also depends on the grain size. Now, the formulas are all nonlinear, and that has a problem in how they affect, or they can be computed, and the uncertainty of the event. Now, the shear rate also, as I said, is not, we are not able to measure that, and it's a function of the hydraulic radius and the energy slope, and is normally calculated with variables as velocity and depth. Now, this plot shows a common formula to relate the water discharge to the sediment rate in tons per day. And as you can see here, it's obtained from data. The points are data for a particular river, and there is a line that is a correlation that was numerically obtained. So the problem with this type of behavior, that is actually a physical behavior, is that this has nothing to do with the models, is that for a particular discharge, you can get the bed load transport rate. That's perfectly fine, and it's an approximation. But what happens is if you have a little error or uncertainty on the water discharge, so a little higher discharge will lead to a much higher bed load transport rate. So this larger change that you can see here, it's an intrinsic effect of the sediment transport process. So little changes in water discharge can generate larger changes in bed load transport, and that's an issue or uncertainty that is generated in any model that uses the formulas to calculate the discharge. So this needs to be looked at an approximation on the determination of how the model behaves. Now, the RiverFlow2D model, as many of you know already, is a combined hydrologic hydraulic model, uses flexible mesh. It can handle dry and wet bed. It uses a finite volume numerical engine that is able to compute supercritical and subcritical regimes. It has several modules: sediment transport, pollutant transport, modern debris flow. It can do hydraulic structures in 2D, including bridges, gates, weirs, and several other structures. And also, the model can work in English and metric units. It's integrated with the SMS graphical user interface, as we will see in a few minutes. And it has a GPU module that can run many times faster than the GPU standard version. Okay, so all of the development that we do at Hydronia is made in collaboration with the computational hydraulics group at the University of Zaragoza. We have a very strong and continuous collaboration that allows us to develop new products and very efficient methods to compute the models all the time. The flexible mesh is formed by triangles that can have any size and can be adapted to any geometry, and also what we compute at the element level are the depth, velocity components, and the depth, and the bed elevation, and the velocity can have any direction. So it's not it's a full two-dimensional model that can handle any direction in the velocity. The main numerical properties of the RiverFlow2D model are several. One is that it's very accurate regardless of the flow regime. The mass conservation is virtually zero or very, very close to zero, 10 to the minus 14% on that order. And also, the numerical solution is insensitive to the time step or the CFL. The time step is automatically computed by the model, so it wouldn't be an issue in any case. There are many tests that demonstrate that the model is very stable, consistent for any realistic situation. Now, in particular, the sediment transport model implemented in RiverFlow2D can do bed load transport, suspended load transport, combine bed and suspended load, and there are situations where you have fine sediment and coarse sediment and requires using both transport mechanisms. You can also use multiple size fractions, which you can both for the suspended load and the bed load. So it's not only a model that can handle a single size of the sediment, but a whole range of sizes can be accommodated. The standard model can normally is coupled, so the hydrodynamics and sediment transport run simultaneously, and there is an uncouple option under testing, which means that the hydrodynamics doesn't need to be computed every time step. Because it does not depend so much on how you change the bed, and that's an option for long-term simulations that run much faster than the coupled version. and it will probably be released in the next year. The governing equations are obtained obtained basically using a balance of the inflow and outflow sediment transport in a control volume. For the bed load, we have the hydrodynamic mass conservation and momentum conservation, and also the bed elevation changes is in the bottom. You see the equation that's called the Exner equation that computes how the bed changes for each fraction based on the fluxes of sediment in two directions. So this is the bed load that can use 10 different formulas for calculating the bed load transport, including Mayer, Peter Mueller, and other well-known formulas that had proven convenient for calculating the bed load. The boundary conditions in the bed load model include, for the upstream, the equilibrium, which is essentially not given any condition for the sediment discharge, but the model computes automatically the inflow discharge of sediment based on the transfer formula that the user selects. But also you can provide the discharge as a function of time for each size fraction. So if you know what is the, or want to evaluate for future versions, what's the inflow discharge, you can also give that upstream. Downstream does not require any condition. Now, some of the assumptions include the following. The transfer rates are based on total bed load formulas. The formulas use a substrate sediment size with no bed armoring. So the model does not compute how the fraction change on the bed. The bed is assumed to be constant in time, not the elevation, but the composition of sediment. In the case of suspended sediment load, we have the same hydrodynamic equations, but the sediment mass conservation equation is based on the advection equation for each concentration for each fraction. So you compute the concentration for each fraction in time and space. And you have also several options for the settling velocity. The boundary conditions for the suspended load model include, for upstream, the concentration for each size fraction. So this is a requirement. So you need to provide each fraction concentration upstream. And downstream, you don't need to provide any conditions. So it's relatively simple to set up a model like this. Sorry. Now, it's very important. One feature that the model provides is the geomorphological collapse algorithm that allows you to provide a friction angle, and with the friction angle, limit the maximum gradient that the bed can achieve. So normally, unless you have a very cohesive sediment, the friction angle dictates the maximum slope that the bed can have, and that is automatically handled by the model to avoid creating unrealistic profiles in the bottom. And this is done with full mass conservation to avoid any intrusion of mass from the algorithm. So it's something that works pretty good for the range of sediment sizes that are accounted for in the model. Another feature that the model provides is the way to give a maximum erosion depth. So you can provide polygons and indicate what is the maximum depth that can be eroded at different locations. For example, if you have a riprap covering, as you have in the right hand picture, or you have a road by the river that cannot be eroded, you can select those areas as areas that cannot be eroded, or you can also have an outcrop in the river itself and determine what's the maximum erosion depth that can be in the river. So it's very useful to account for areas that are not able to be carried away by the flow. So it is assuming that obviously not all areas are erodible in the model by using this option. Okay, so we have some questions coming up. I'll take care of the questions at the end of the webinar. Now, in regards to verification and validation, there have been many tests done on the model. These are just 3 papers that we are referring you to if you were interested in looking at the different test and algorithm details that we implemented in the model. And they include a wide set of tests where the model is compared using data from real events and so forth. This is an example from the last paper that I showed you in the previous page. It's in the bottom by Sierra Casta, which one of our collaborators at the University of Zaragoza. And this is a case of dam breach overtopping. So you see on the left the Toast Dam that was, this is a real event that occurred in Spain in the mid-80s. And you see on the right the evolution of the dam as it erodes and the velocity on the left. So the model can handle this type of very, very rapid events because it's coupled and can handle situations of supercritical flows that they occur in these rapid change situations. Now we have a couple of ongoing developments. One of them is the GPU implementation of sediment transport model. And what this means is that you can go from a very slow car on a CPU model to the fastest car on Earth as the GPU version. And this is as dramatic as that. I'm not exaggerating. I will show you some numbers. It's presently offered as a service only. But eventually it may become actually a commercial product. But if you have the need to run a very long-term simulation, we have the servers with the right GPU cards that can accelerate your run significantly and help you be more productive in your model. So you can do all the setup of the model, and then we do the run, and you can just look at the results, and you will get that in a fraction of the time that it will take to run with any processor in CPU mode. For example, this is an example of erosion following a dam break from the paper I mentioned. And here you have the times in minutes. With CPU 1 core, it takes 108 minutes. With 4 cores, it takes 38 minutes. And with the GPU version, it takes 1.92 minutes. So this is a significant change. Of course, times is in minutes. It's not that long anyway, but it's a big change because it means that you can make much more runs than that you would make if you don't use the GPU version. In the case of the 4 cores, you get 3 times faster than the 1 core version, but you get 56 times faster with the GPU. In practical terms, this means that a run that would take 2 hours can be done in 2 minutes in the GPU. It's that dramatic, the acceleration that you get with the GPU version. Another more realistic case, the Toast Dam that I showed before. This time the times are in hours. 207 hours are required to run
here, and it seems that
the
my sound
model
went away.
in
I hope you can hear
4-core
me
GPU, CPU. While it takes only 8 hours using the GPU version on an NVIDIA GeForce Titan Black. Now in this case, the acceleration
Can you hear me back?
is very, very important.
Okay,
and
I
has
apologize for that.
tremendous implications for
I don't know what
project
happened,
work.
but the sound suddenly
in these
discontinued.
situations, we have an acceleration
well, in the case of the erosion
207 hours.
of the Toast Dam,
just imagine what that means to only 8 hours.
So the timings are
in the time that you do only one simulation with 4 cores, you can make 26 simulations
8 hours
with the NVIDIA
Titan Black
GPU version.
So
it's 26 times faster.
Big,
so
a big
In the
change
previous
and
example,
a
we
lot of
were
improvement
running in minutes
based
instead of
on
hours.
the
And in this particular case, we can run instead of days,
okay,
we can run
based on
the same thing
use of
in
the
hours.
GPU version.
So instead of
So in practical terms,
having
again, this means
8
that
days or almost 9 days to make a run, we can complete that run
a run that
in just
may
8
take
hours. And this
8
is
days or
very
more than 8 days
common and
with the
typical
CPU
of
version.
the
It
simulations that you
reduces
get
to 8 hours.
with the GPU
So with the GPU version, you turn out reduces times from days to hours and from
Okay,
minutes to seconds
let's move on.
and so forth. So it's really impressive, the advantage of using the GPU version. Okay, so let me start now with the example that I want to show you on the how to implement a sediment transport application. It all starts by opening the SMS graphical user interface. And this is what we are trying to do today. We then import the elevation points, define external boundary polygon, then we'll define the boundary conditions, inflow and outflow, enter the run control parameters, how many parameters you need to run the model with sediment transport and so forth, sediment transport data, and then run the model and finally visualize results. So we'll try to cover this step-by-step process. Okay, so this is the SMS user interface. So what we start doing is I'm using a example that is actually a real case, and I will first load the RiverFlow2D template, and I will load also the RiverFlow2D map file that includes a number of coverage or predetermined coverage that you can use to populate them to enter data in the model. Now I'm going to use a projection here because this site is in California, so I'm using a state plane, California Zone 5, and this is important when you try to output the results especially for Google Earth or some other georeference mapping software. And I'm using feet as my system of units here. Okay, so I have my basic RiverFlow2D environment created. I will import now the bed elevations, and I'm using the import wizard. This is a very convenient way to enter data in many different formats, and I can color this based on the contour scheme. So I'm using rainbow scheme here so that this is useful to understand what the points means. The blue mean the lowest elevations. This is the main channel. And in this particular river, this is in California, as I said, this is the inflow upstream and the outflow downstream. You can also import an aerial image. So I'm importing a JPEG image for the background. That is useful also to enter data. Now I'm turning that off because I want to now enter the boundary polygon, and I will do that without the image in the background. It's easier for this particular case. So I'm entering this polyline here, another polyline for the inflow boundary, this lower solid boundary here, and lastly the downstream boundary here. Okay, so now we have this external polygon. I will select all the polylines that I created, and I will redistribute the vertices, because these vertices are spacing is the one that the SMS uses to refine the mesh or create the mesh here. Okay, now the next step is to enter the boundary conditions. I will use here, selecting the upstream boundary. I select the attributes for an external or exterior boundary condition of discharge, and I will use here a discharge of 30,000 cubic feet per second. And downstream, I will use a uniform flow condition, also is exterior boundary, with an energy slope of 0.0025. Okay, now that I have the boundaries ready, I will build the polygons so that SMS understand that this is the internal part of the polygon that I need. So this is the polygon that will be the focus of the mesh, and I need to link this to the scatter set that represents the elevations. Is the bed elevation layer here. And I will use extrapolation with inverse distance weighted option, just in case there are points outside. And essentially, that's all I need to create my model. So I will call this Sediment Transport 1, just to save it. And I will create the mesh now. So far I haven't entered any data for the sediment transport. I'm just, let me color this so that I can see the contours. So these are the interpolated elevations at the node level or the cell level. So I can see they represent correctly my terrain. And now we're ready to go ahead and perform a first simulation. I will change in the global parameters here. I will add bed load sediment transport. So I will use only one fraction for this example. I'm using here the Mayer-Peter-Mueller formulation. The sediment density, in this case, is in English units, is 165 pounds per cubic feet. I will leave this default of 0.001 as the diameter of this fraction, porosity 0.4, shield stress, etc. I leave the rest as defaults, so as they are fine for this example. And I will save and make my run. Now the run opens the sediment transport dynamic module, as you can see here. It runs very quickly. It's only 1 hour. It's just test run. You see here the mass conservation error is 1.8 to 10 to the minus 14%, which is virtually negligible. Water inflow, water outflow, sediment inflow, sediment outflow. So this is not steady state, obviously. It's only 1 hour run. Now I want to show you what you can do next, because what this allows you to do when you use the data input program in the RiverFlow2D data input program, you can change your sediment transport mode. You see you have suspended sediment that is not turned on here. You have bed load sediment. You can change your sediment transport formula here. You can add more fractions here. You can add as many fractions as you want or remove them. Add the data to each one of them. The same with the sediment size fractions for the suspended sediment. Now let me just run the model again. With a little more time, I would just put 6 hours here, just so you have an idea of how this looks like. Let me save this data. So now the model should run for 6 hours. You see how quickly converges the hydraulics. The sediment transport is much more slower to converge because you may have erosion coming from here that is increasing the outflow of sediment and so forth. But this gives you an idea of how fast you can set up a model from scratch. Again, this is not an animation. This is just the actual model running with the data that you have access to. Now, when the model terminates, it creates a number of files that you can use for post-processing, including the HDF5 files. And let me import those files here. So these are the result file. Now the results files allows you to see different, this is water surface elevation as they change in time. But you can see also variation in depth. These are changes in bed elevation. So you see here that as I move down in time, you have areas of erosion depicted here in dark blue, and areas of deposition depicted here in yellowish or reddish color. So you can look this in 3D perspective as well. You can do a lot of things here with the SMS interface. You can, for example, create if you, for example, if you turn on the image here, you can map the do a texture mapping. So you have your terrain, your aerial mapped to the terrain, and you can look at that in 3D. So it's quite neat to the visualization things that you can develop in SMS. You can remove and create transparency here. For example, I can remove all the elements. I don't need them anymore. And I can also add a little transparency. So you can see now the 3D terrain with the overimposed changes in bed elevation or depth or any other variable you want. Now you can also look at the maximum results, and the maximum results allow you to visualize a number of features, like, for example, the maximum bed elevations that were obtained during the simulation, the maximum changes in bed elevations. So this map shows areas that suffered the maximum deposition and maximum erosions, and etc. So you have the full set of results that you can get from the model, from the sediment transport model. Now let me show you a very useful feature that you find in SMS, is that you can draw profiles and extract profiles from the area. So let me turn off here the image, and let me use the profile coverage to enter a profile. So I will create a profile here, and I will you can also create cross sections. For example, here you can let me create here a cross section, another cross section here, for example. Okay, so with that, what you can do is to plot what's going on along those profiles. So in the display menu, you have the plot wizard, and you can look at the observation profiles. In this case, I want to show you, for example, what's going on with the bed elevation versus the initial bed elevation. So what you see here is the profile of the bed elevation and the actual bed elevation. So this is the initial bed elevation here, and this is the bed elevation after 5 hours and 18 minutes. So you can have a lot of flexibility in looking at what's going on with your results and generate this. You can also view the values, export these values to a spreadsheet for different processing if you want. And also you can do the same for the cross sections. For example, you can use again the plot wizard, plot for the cross sections. Let me look at one of them one at a time. So you can look at the, let's say in this case, bed elevation and initial bed elevation. So you can see here how a particular cross section is changing in time during the simulation. So there are areas of the cross section that are getting deposition, some are getting erosion, some are not changing at all. So probably this is because this is the dry cross section, the dry cross area that is crossed by this cross section over here. So it gives you a lot of tools that you can use to visualize your model results. So hopefully this gives you a general idea of what you can do with the model. And again, I have used actual data and an actual model setup here from scratch. So once you master the user interface, it's not difficult to set up a model for sediment transport simulations. So let me go back here to my presentation. I have a couple of things that I wanted to share with you. Again, it's about the licensing, because I want just to mention that in particular we have a special offer that is valid until the end of this year, and the offer means that for new users, for the price of the single user basic license, you get all the modules. So you get the sediment transport module essentially for the price of the basic license, which is a very good deal. And also for those users who already own the license of the model, you can get a 35% discount on the sediment transport add-on module. So this is it's a pretty good offer that ends at the end of this year. And again, with the purchase of the license, you get a full year of technical support, online training, a 2-hour online training included, and also all the upgrades that occur during the year. With that, I'm running out of time, so I wanted to take a couple of minutes to answer some questions. I apologize for the difficulty we have with the sound. I don't know still what happened, but hopefully the recording occurred. I'm not sure if that happened or not, but I will check out later. Okay. I have a question here. Uh, is there an option to apply sediment transport computation after water condition reaches a steady state? Yes. Yes. Yeah, you can do a only water simulation. It reaches a steady state, and then you use a hot start. So that when you finish that only water simulation, you get files that represent the snapshot of the steady state hydraulics. And then you start a sediment transport with a hot start option, and that will use your stored steady state simulation as the initial conditions for the sediment transport. So yeah, you can do that. Um, okay. What is the runtime like using the ST module without a GPU? Well, unfortunately, we didn't have sound when I was presenting this, but these results are let me go back here a little bit. Okay. Okay, so this is a real case of erosion following a dam break. So with this will be the ST module for CPU only using 4 cores. It takes 38 minutes for this particular event and 2 minutes for the GPU. Now, in a more realistic case, is the erosion of the Tulsa Dam. It takes, well, 8 days for eroding the whole dam here, and it takes 8 hours in the GPU. So it's a significant change in the um, in the output the time run times. Well, I think I ran out of time. Well, let me answer this last question here. Can I run the model on a computer cluster? Well, you can. If the cores are visible to the Windows environment, you can use that for parallelization. If the cores are not visible, then you will only be able to use the cores that are available for the operating system. Now, in theory, also we have you can use different processors for the GPU version. So you have multiple cards. You cannot use the multiple cards for a single run, but we are implementing a way that you can run different scenarios in each of the cards that are available. So that's another option that you could explore. Well, that's all for today. Unfortunately, I ran out of time. I will check what happened with the sound, and hopefully the recording came out okay. And we'll try to fix it for the recording. So thank you all again. Have happy holidays. I wish you the best for next year, 2016. And hopefully we'll start early in the year with new webinars in this series of Hydronia webinars. Thank you so much.